the condenser. Master of heat rejection, today we explore the condenser, the unsung hero of refrigeration that performs the critical task of rejecting heat from the system. While the compressor gets attention as the heart of refrigeration, condenser quietly handles one of the most challenging aspects of the cooling process, efficiently removing heat from high-temperature refrigerant and releasing it to the environment. Historical evolution of heat rejection. The concept of condensation for refrigeration traces back to the earliest cooling systems. William Cullen demonstrated artificial refrigeration at the University of Glasgow using a small amount of diethyl ether, which required a condensation process. However, practical condensers began with the work of Jacob Perkins in 1834, who received the first patent for a vapor compression refrigeration system using liquid ammonia. Early condensers were remarkably simple, essentially coiled pipes immersed in water or exposed to air. The first commercial ice-making machines of the 1850s used massive water-cooled condensers, often requiring entire cooling towers or access to natural water sources like rivers or lakes. These early systems were incredibly inefficient by today's standards, but they established the fundamental principle that heat rejection efficiency directly impacts overall system performance. The 1920s brought significant advancement with the development of fin-tube condensers. Engineers discovered that adding fins to tubes dramatically increased the surface area available for heat transfer without proportionally increasing size or cost. This innovation made air-cooled condensers practical for residential use, eliminating the need for water cooling in home refrigerators. World War II accelerated condenser development as military applications demanded compact, efficient cooling systems for electronics and food preservation. Post-war prosperity drove demand for better home appliances, leading to the development of more sophisticated condenser designs that balanced efficiency, cost, and reliability. The mechanism of heat rejection. The condenser's operation involves both sensible and latent heat transfer, a sophisticated thermal process that occurs in 3 distinct phases. Understanding this mechanism reveals why condenser design is so critical to system efficiency. In the first phase, superheated refrigerant vapor enters the condenser at high temperature and pressure from the compressor. Initially, the condenser removes sensible heat, cooling the vapor from its superheated state to its saturation temperature. During this phase, the refrigerant remains in vapor form, but its temperature drops significantly. The second phase involves the actual condensation process, where latent heat removal occurs. As the refrigerant reaches its saturation temperature, it begins changing from vapor to liquid while maintaining constant temperature. This phase change releases enormous amounts of energy, the latent heat of condensation, which must be efficiently removed by the condenser. This is where the majority of heat rejection occurs and where condenser efficiency is most critical. The third phase provides subcooling, where the condensed liquid refrigerant is cooled below its saturation temperature. This subcooling ensures that only liquid refrigerant reaches the expansion device and provides additional system efficiency by increasing the refrigerant's cooling capacity in the evaporator. The heat transfer process relies on 3 modes: conduction through the tube walls, convection to the cooling medium, and often radiation to the surrounding environment. The condenser must facilitate all 3 modes efficiently while managing refrigerant flow and pressure drop. Types of condensers. Diverse solutions for heat rejection. Air-cooled condensers dominate residential and small commercial applications due to their simplicity and independence from water sources. The most common type uses copper tubes with aluminum fins, arranged in configurations that optimize airflow and heat transfer. Natural draft air-cooled condensers rely on buoyancy to create airflow, while forced draft units use fans to move air across the coils. Modern designs incorporate microchannel technology, using smaller tubes and enhanced fin geometries to maximize heat transfer while minimizing refrigerant charge and size. Water-cooled condensers offer superior heat transfer efficiency and are preferred for large commercial and industrial applications. Tube condensers use refrigerant flowing through tubes surrounded by water, while tube-in-tube designs work well for smaller applications. Plate heat exchangers provide compact water-cooled condensing with exceptional efficiency. The key advantage of water cooling is water's superior heat capacity compared to air, allowing for more compact condensers and better control of condensing temperature. Evaporative condensers combine the benefits of air and water cooling by using water evaporation to enhance heat rejection. These units spray water over the condenser coils, while drawing air through the wetted surface. The evaporation of water provides additional cooling beyond simple air cooling, significantly improving efficiency in hot climates. However, they require water treatment and maintenance to prevent scaling and biological growth. Modern condenser innovations. Today's condensers incorporate sophisticated technologies that dramatically improve performance and reliability. Microchannel heat exchangers use parallel flow designs with smaller refrigerant passages, reducing refrigerant charge while improving heat transfer. These designs also enable aluminum construction, reducing weight and improving corrosion resistance. Variable geometry condensers can adjust their effective surface area based on operating conditions, optimizing performance across varying loads and ambient conditions. Smart condensers incorporate sensors and controls that adjust fan speeds, water flow rates, or damper positions to maintain optimal condensing conditions while minimizing energy consumption. Enhanced surface technologies include internal and external fin enhancements that increase heat transfer coefficients. Hydrophilic coatings on evaporative condensers improve water distribution and heat transfer. Advanced materials like titanium tubes provide superior corrosion resistance in harsh environments. Conclusion: the condenser represents a perfect example of how fundamental physics principles, heat transfer, phase change, and fluid dynamics combine in practical engineering solutions. From the simple coiled pipes of early ice machines to today's sophisticated microchannel designs, condensers continue evolving to meet growing demands for efficiency, reliability, and environmental responsibility. Whether it's the finned coils behind your refrigerator, the radiator-like unit beside your air conditioner, or the massive cooling towers serving industrial facilities, condensers quietly perform their essential function of heat rejection that makes modern refrigeration possible.